CDNO has half-life of about 1 hour. Okay. So first I wanted to look at how nitric oxide will affect the bacterial membrane. And to do this, I used transmission electron microscopy, or TEM, to visualize the cross-section of the bacterial cells. So very briefly, this technique, we have an electron beam that passes through a series of lenses to hit a specimen, and the transmitted electrons then go through more lenses and finally captured by a detector as an image. And this method provides very high resolution, and therefore can be used to visualize the bacterial membrane, but it requires very thin specimens so that the electron beam can pass through. And so for the sample prep, I first treat the bacteria at lethal doses of NO. Then I fix the bacterial cultures with glutaraldehyde to cross-link any proteins and preserve them from subsequent sample prep. I stain the bacteria with a metal dye, osmium tetroxide, dehydrate them with ethanol, and then embed them in epoxy before cutting using a knife, a diamond knife, to cut very thin slices, about 60 nanometer slices. For reference, bacteria is about 1 order of magnitude thicker, 1 to 3 microns. Okay. So first, we have untreated gram-negative bacteria shown here, Klebsiella pneumoniae and Pseudomonas aeruginosa. You can see that they have intact cell membranes with no spillage or disrupted membranes. When I added Sperno and CDNO, you can see a heavy disruption of the bacterial cell envelope. The bacteria lose their shape, and there's some spillage of the cytoplasmic content. Now, for gram-positive bacteria, Staph aureus and Enterococcus faecium, untreated, you also see like an intact membrane, and you also can tell that the membranes of these bacteria are thicker, visibly thicker than the gram-negative, and this is due to the thick peptidoglycan layer. So what I found was interesting was that when I added NO treatment, there was no visible changes to the bacterial cell envelope. And I went further and tested this with see if different NO release kinetics will have the same effect. And what I found was that regardless of the NO kinetics, Papa NO being the fastest and DPTA NO being the most extended release, Klebsiella pneumoniae, so gram-negative bacteria, had their membranes disrupted, whereas Staph aureus, the bacterial cell envelopes were not affected. I also tested with a few drug-resistant strains and saw the same result. Again, gram-negative was affected, and Staph and gram-positive was not affected. So, I think regardless of the treatment condition, it appeared that the gram designation was the main factor that led to the bacterial cell effects. So that was looking at the cross-section of bacteria. Now I want to look at the sort of the exterior of the bacterial cell, and to see how, specifically to measure the surface roughness. And this is important because increased surface roughness is usually correlated with increased membrane damage. And to do this, I use atomic force microscopy, or AFM. And how this works is we have a nanometer size metal probe with a laser shining on top of it that can be detected by a photodiode. And as the probe lowers onto the sample, it will bend and get deflected, and this deflection can be measured by the laser spot to produce an image. For the sample prep, I first start with a layer of mica, which is a silicate material that is atomically flat. I then add a layer of polylysine to provide a positive charge.